Okay, good afternoon. My name is Kristian Thygesen, and I think I'm sharing this session, even though I'm also the first speaker. This session is about high throughput screening or high throughput calculations and data quality. And the program will be at first there will be a talk by myself about computation screening of light harvesting energy materials, and then there will be a talk by Mikkel Strange on estimating errors from high accuracy DFT calculations, so errors on DFT calculations. And then there will be a talk by Sten Lysgaard from ETU Energy, which will introduce the genetic algorithm, which is a method for global structure optimization. And he will also introduce the hands-on tutorial, which will take place after these three talks, and which will be about genetic algorithm approach, where we try to use that method to calculate the convex hull of a surface alloy. Okay, so I think we should just get started. So I'm part of this NOMAD Center of Excellence that I'm sure you've heard already something about. And the task of NOMAD is put up here. It is to develop a materials encyclopedia and big data analytics and advanced graphics tools for material science and engineering. And this project is building on top of a repository, the NOMAD repository. And last year, myself and my colleague Kristian Thygesen wrote a perspective in science about computational screening of materials and big data approaches in material science. And we made this view graph, which is showing the number of DFT calculations stored in the NOMAD repository. And we were a little bit concerned about the flattening out. Over here you can see in 2006 the number is sort of staying at 3 million. But you can see today there is actually 44 million DFT calculations in the repository. So it's a huge repository that is growing at a tremendous speed. So I think it's very appropriate to have this school here on how can we use machine learning methods and how can we take advantage of all the data that is stored in these databases. And of course, one of the issues when you're going to use computational materials databases is the data quality. So can we trust the calculations that are in the repository, which is produced by many different codes and using many different parameter settings and so on. And that will be the topic of the next talk that Mikkel Strange will be talking about. So I'd just like to mention that there are other materials repositories around. We are developing one ourselves at ETU Physics called the Computational Materials Repository, which is a much smaller scale kind of database where you're not able to upload from outside. So it's something we're using internally for storing the results of our research projects. So we are uploading and organizing the data here, and then you can go and you can look at the different projects there, and you can download all the data from the different projects. So it's a much smaller scale than the NOMAD repository, a very different type of database. Okay, so the scientific case that I'll be discussing today and that I'll be using to illustrate the concept of materials screening, computational material screening, is that of hydrogen production using solar energy. So there are basically two ways that you can convert solar energy into hydrogen. One is you use first photovoltaics, solar cells, to convert the solar photons into electrical energy, and then you do some electrochemistry, electrolysis, to convert the electrical energy into hydrogen by splitting water. So that's a process that has or can have an efficiency of around 10%. The other possibility is to cut out the middleman here and try to produce hydrogen directly. So this is called photoelectrocatalysis. So solar light is coming in, and one is directly producing hydrogen by splitting water. So that's a much more challenging process, and actually today it's something that is not really viable because we don't have the right materials at hand to catalyze the reaction and to absorb the solar photons. So I put a question mark in here because it's unknown at present what the efficiency of such a method is, but let's try to take a look at how this photoelectrochemistry works, or photoelectrocatalysis works. So solar light is coming in, photons are absorbed in a photoabsorber, and then that's converted into electron hole pairs that then go to the surface here, split water, so we have oxygen bubbling up on one side, and we have a proton going through a membrane, and over here we are reducing that H plus into hydrogen. So that's the basic principle. And we can break this down into three parts here. The first one is the photoabsorber, so we need to absorb the solar photons and convert them into electron hole pairs. The next one is to produce the protection layers here, because it turns out that such photoabsorbers are not going to be stable under these conditions. They are very likely to oxidize, so we need to protect them. So there is a problem of finding corrosion-resistant protection layers here to protect the photoabsorber, and then we need catalysts. We need catalysts here for catalyzing the water splitting and the hydrogen evolution reactions. And what I'll be focusing on today is the photoabsorber problem. And specifically, I'll be interested in this tandem device, where instead of having just a single semiconductor with a given band gap, we are combining two semiconductors, one with a large band gap that is absorbing high energy photons, and then there is a low band gap material here which is absorbing low energy photons. So we need two photons to create two electron hole pairs. But this electron here, if the potential difference is correct, can move over and reduce this hole, and then we are left with one highly energetic electron hole pair. And that's important because in order to drive the water splitting reaction, we need around 2 electron volts for that reaction. And if we just use a single photoabsorber, we need a band gap of at least 2 electron volts, and that means we can only harvest a relatively small fraction of the solar spectrum. So we can take a look at the efficiency of such a device here, plotted as a function of the top absorber band gap, so the large band gap material. And the blue curve here shows the efficiency as a function of band gap if we have a single photoabsorber material. And you can see that this peaks at around 7% here at a band gap of around 2.3. If we combine a large band gap material with silicon, which has a perfect band gap for absorbing solar photons at the low band gap side here, with a band gap of around 1 eV, then you can see we can reach efficiencies of about 20%. And in that case, we need a band gap material here, a material with a band gap of around 1.8. So that's the challenge. The problem is that right now, as of today, there is no material that is efficient in creating a 2 electron volt or creating a 2 volts photovoltage. Right? So we really need materials with band gaps around 2 electron volts in order to make such a tandem device. So if we look at materials that are already known, we can see here they are the conduction bands and the valence bands are plotted here relative to the redox potentials of the water splitting potential here, the hydrogen evolution potential. So we need the conduction band to be above this potential. We need the valence band to be below this potential here if we are looking for a single material photoabsorber. We can see silicon here is actually quite useful for as low band gap material. It has a conduction band that is above the hydrogen evolution potential. So that would work for that hydrogen evolution reaction. Then over here we have all the oxides, and you can see the band gaps are generally too large and the valence bands are lying too deep. But then we have the sulfides here, and they actually have valence bands. They have smaller band gaps closer to the 1.8, and they have valence bands that are actually closer to the oxygen evolution potential down here. So looking at sulfides is probably a good strategy. And so with that in mind, we looked for sulfide perovskites in the stoichiometry of ABS3. And if you just take the periodic table and you say how many combinations, how many materials can we make if we let A and B be any metals in the periodic system here, then it's around 3,000 combinations that we can find. Okay, so if you just take at random 2 metal atoms and put them together with 3 sulfurs, then most likely you will violate the valence rule here, and that material that violates the valence rule is not going to be stable. Okay, so if we also incorporate the valence rule here, so we say that the oxidation states of the A and the B atom have to sum up to 6, because sulfur will usually take 2 electrons, and we have 3 of them, so they have to sum up to 6 here, and then we are down to 705 compounds that satisfy this rule here. So now we're doing a computational screening, and the computational screening is illustrated by this screening funnel here. So if you start, you have a number of criteria that you want to evaluate. One is stability, another is band gap. Effective masses could be another quantity of interest, because you want to have low effective masses in order to have high mobilities. The electrons and holes that are created have to reach the surface of the material, and you want the material to be defect tolerant. This can be calculated, all of these properties, using DFT, but some of them are much more computational demanding than others. So it makes sense to apply this screening strategy where we start with the simplest criteria, and the materials that do not fulfill this criteria are then excluded up here. And then as we go down the funnel, we have fewer and fewer material candidates, and we evaluate properties or functionalities that require more and more expensive calculations. So that's the idea behind this computational screening approach. So since we are interested in semiconductors, we started out with the 700 candidates here, and then we did DFT calculations of the band gap, and I should say that all these calculations are done with the GPAW electronic structure code, which is a PAW plane wave code. It's an open source project, and you can download that code freely under GPL license. Right, so what I wanted to say is that we start up with cubic perovskite structure, and then we calculate band gap. But the band gap is very sensitive to the structure. And it turns out that if we take the 700 perovskite in the cubic structure and we calculate how many of those have a band gap, we find that only 25 have a band gap. So most of them are metallic. That might seem surprising. And indeed, after letting the structure here relax into a distorted cubic structure, then 200 of the structures actually have a band gap. So this shows this extreme sensitivity of the band gap, or the band structure in general, to the structure of the material. So relaxation, and in particular, if the system wants to undergo symmetry breaking distortions, that could influence the band gap of the band structure quite dramatically. Okay, so out of the 700 compounds, when we do this simple distorted cubic perovskite, around 200 of them have a band gap. Okay, so we throw out all the materials now that do not have a band gap in the distorted perovskite structure. So we're left with 200 stoichiometries. Then we go to the ICSD, and if we search for structures with a ABS3 chemical formula, we find 225 structures in this inorganic crystal structure database. These are all experimental crystal structures, and they come in 28 different structures. So out of the 28, we pick the 6 most frequently occurring structures, and then those are the structures, together with the distorted perovskites, that we're considering for the remaining part of our screening procedure. So we have now roughly 200 times 7 different compounds to look at. Okay, so now we did the check for semiconducting structures. We decided on which structures to use for the screening, and the next step is the stability. So the thermodynamic stability of a material is estimated using the convex hull, and you can see the formula up here for calculating the convex hull. So what you do is you're looking at all the possible, for a given stoichiometry A, X, B, Y, just to take a binary example, you look for all the possible phases you have which contain A and B atoms in some stoichiometry. And then you form linear combinations of these phases with expansion coefficients that have to be positive and have to obey the conditions here, so that they in total have the same stoichiometry that you're interested in. Okay? So this will tell you if your material now has an energy above this convex hull, it means that it's energetically more favorable for the material to segregate into these different phases up here. So you will end up with a phase segregated compound. Okay? So thermodynamic stability at a given stoichiometry is then guaranteed if the material is lying on the convex hull. So all the dots up here are above the convex hull. In this case, this is aluminum oxide as a function of the amount of aluminum in here. So all the phases up here will be thermodynamically unstable. Okay, so for all the compounds that we have at present, we calculated the convex hull, and we did that by taking the OQMD database, which is a database that has vast calculations for, I can't remember how many thousand compounds. So there are a lot of binaries, and there are also quite a lot of ternaries, and a lot of ternaries also from the ICSD database. So we simply took all the materials from that database, and we calculated the convex hull for our ABS3 structures. And then we evaluated the energy of the 7 phases, the 7 structures that we are interested in, and compared it to each other, and compared them to the convex hull. And here you can see the result for just a few of the ABS3 compounds. For example, over here, you can see that the black symbol, that's the hull energy, that's the convex hull. And you can see in this case that all the 7 structures we're looking at here have an energy that is higher than the convex hull. So in this case, we will discard niobium, copper, sulfide, and not work anymore with that material because the convex hull is actually, or all the structures we are looking at are thermodynamically unstable. Okay? But if we look over here, you can see there is 1, 2, 3, 4, 5 of the structures we are looking at, and all of them are more stable than the convex hull. Okay? The convex hull, of course, the real convex hull would then include the most stable of these structures in reality. But this is what we're looking at here is an approximation to the real convex hull, which is produced by the materials that happen to be in the OQMD database. And clearly, that didn't include the materials that we're looking at here. Okay, so in this case, we will keep all these materials here. You can see there is an error bar in the DFT calculations. And Mikkel will talk more about how to make this error bar in DFT calculations, but I just want to say that these calculations are done with the so-called beef functionals. And the beef functional works with an ensemble of enhancement factors for GTA functionals. And the width of that ensemble of enhancement factors has been determined by comparing the result of DFT calculations to experiments, right? To known experimental structures. So this error bar here says something about the error coming from the GTA approximation. Okay. So there are a couple of things to note here in general, that typically there are many structures that have very similar energies. We should also bear in mind that when we're looking at these materials at finite temperatures, there are entropic effects that will really change the energetic ordering of the different phases. So what we do is we decide to keep structures that are within 25 millieV per atom of the most stable phase. Okay? So that means that in these cases here, we will probably include, let me see, a couple. Over here, we will only include one material because there is one material that is more stable than the rest of the materials by at least 25 millieV. Okay? So that's the way we decide on stable structures. Okay, so now we have a number of stable materials. Next step is to consider the band gap of these materials. And as you might know, then DFT with some of the most widely used exchange correlation functionals is not very good at predicting band gaps. But we have found that using this GLBSC functional, which is not a very well-known exchange correlation functional, then we can actually get quite good agreement, you can see over here, between the calculated band gaps from theory and those from experiments. This is now tested for a range of metal oxides. The crucial thing with this exchange correlation functional here compared to other exchange correlation functionals is that this functional actually allows you to estimate what is known as the derivative discontinuity. And there is a fundamental theorem that says that the true quasi-particle band gap of a material is the cone-sham band gap, which is in general not the correct band gap, but the cone-sham band gap plus what is known as the derivative discontinuity. And typically, the derivative discontinuity is either predicted to be 0, that's the case with all the semi-local functionals, or the functional doesn't prescribe how to calculate the derivative discontinuity. So that's the difference of that functional from other functionals, and you can see that this is another test where we looked at 20 randomly chosen systems from the ICSD and calculated band gaps with a range of different methods, as you can see up here, and the mean absolute error of all these methods compared to fully self-consistent GW calculations is shown over here. You can see the CLLB-SC, which is really not much more expensive than a GTA calculation, is within 0.4 eV of the GW result, which is not perfect agreement, but it's acceptable for a screening study. So using that functional, we're now calculating the band gap of all the materials that are left in this screening study. And you can see again here the different phases, the different structures we're interested in, and this is just a subset of the materials that we have at this point of the screening. And we have the band gaps here of the most stable structures. There might be more than one structure if they are within 25 millieV in stability, then we have more structures with the same stoichiometry. So for example, here is silver tantalum sulfide. You can see there is only one material here. In this structure up here, you can see that has a band gap of 0.7. So that's something that could be interesting for photovoltaics with a single semiconductor absorber, so we keep that. So the blue window down here are materials that would be interesting for single crystal photovoltaics, and the green up here is large band gap materials for tandem cells, okay, which is our main interest. So you can see there are cases here that are a little bit problematic because there are 3 stable structures here, and they actually have 3 quite different band gaps. Okay, so what to do in this case? That's a difficult case. There are other cases, for example here, where there is only one structure here with one band gap, so there we're more sure about what we could expect. But anyway, these are all the band gaps that we calculated. And next step is now to consider effective masses. And the effective mass is defined as essentially the second derivative of the band structure energy with respect to the wave vector k at the bottom of the conduction band or the top of the valence band. And that's interesting, the effective mass, because it's directly related to the mobility. And you want to have high mobilities because you want the charges to reach the surface to do the chemistry, or to collect the charges if you're interested in photovoltaics. So you can see there's another parameter up here, which is the relaxation time of the material. This is a parameter that is very hard to calculate from first principles. It depends on how many impurities do you have in the material. It depends on electron-phonon coupling, and so on. So this is something we will have to assume is the same for all the materials, and then we will use the effective mass as a descriptor for how high the mobility is. And what we choose in the screening is to take only the materials that have effective masses for both electrons and holes that are lower than 1. Okay? So that's a criteria we set. So all these materials in here represent hopefully high mobility semiconductors. Okay, the final thing we have here in the screening funnel is what I call defect tolerance. So in reality, defects play a very important role, probably a much more important role than we would like to believe as theoreticians, because defects are difficult to treat. In DFT calculations, they require large supercells, and therefore typically, at least in these high throughput screening studies, defects are typically not taken into account. However, they are really important. Here you can see an illustration, just a cartoon of what happens if you photo-excite carriers. So very quickly, these carriers will relax in the conduction band and the valence band to form some quasi-equilibrium distribution. But then after a few picoseconds, those electrons and holes will start to recombine non-radiatively through defect states in the band gap. So if we have states that sit in the band gap, they will act as scattering sensors and therefore reduce the transport properties of the material, and they will act as recombination sensors, where we will basically lose the electron hole pairs that we've generated by the solar photons. So, ideally, we would like to have materials that are robust against the formation of states inside the bandgap. And this is what we call defect-tolerant semiconductors. Okay? So what we did is we took all of the materials that we have left at this point of our screening, and we simply created sulfur vacancies and vacancies of the A and the B metal atoms, and then we calculated the band structure and looked for states inside the band gap. And here you can see here for barium zirconium, there is a case where for all the different defects, we still have our electronic structure of the pristine system present, so there are no localized states in the band gap, whereas for this case over here, you can see the formation of localized states in the gap. So this is really a killer for optoelectronic applications of this material, and we exclude all the materials that form deep mid-gap states at this level of the screen. Okay, so at this point we're actually through with our screening funnel, and we have a list here of around 20 candidates. You can see here the calculated band gap with the GLLB functional. This is the direct band gap, so if the numbers are the same, we have a direct band gap of the material. This is the HSE band gap, as you can see over here for comparison. These are the effective masses, and this is the structure prototype that came out. Some of the materials up here are highlighted in bold. That's the material where there is only one structure that is significantly more stable than all the others. Okay? So that's where we're really sure, or we are most sure, that this is the structure that will actually come out if we try to synthesize bismuth lithium sulfide. In the other cases, there is at least one other structure that is within 25 millieV per atom, as stable as this material here, and which might then have a different band gap. Okay? So we showed this list to some of our experimental colleagues. They looked at it and they said, yttrium lanthanum sulfide, that sounds interesting. We could probably make that. And they went to the lab and they managed to synthesize that material. And using XRD, they confirmed that the structure they obtained was actually the one we had predicted. And they confirmed that the band gap from absorption spectrum here was 2 electron volts. And they also confirmed from the very strong photoluminescence peak here at close to 2 eV that this was a direct band gap material as predicted, and that defects were playing a minor role. Because if you have too many defects here and you have states inside the band gap, then the photoluminescence peak will be dramatically lowered. So the intensity of this photoluminescence peak here strongly suggests that it's close to being a pristine semiconductor. There might be defects, but they don't introduce localized states in the gap. Okay, so let me conclude here. So what I showed you was an example of a computational screening study where we looked at, to begin with, around 3,000 perovskite sulfides. We managed to reduce that to 20 candidates based on the stability of the compound, and we looked at 8 different structures that we were inspired to pick based on the frequency of occurrence of these types of sulfides in the ICSD database. We looked at band gaps, effective masses, and defect tolerance. The lanthanum yttrium sulfide was then successfully synthesized, and what we're doing now, or the experimentalists are doing now, is looking at integrating this material with the silicon low band gap photoabsorber with the aim of using that as a tandem solar cell, or perhaps even for 2-photon water splitting. So, is this a success? Well, I think that just the fact that the experimentalists managed to make this material and confirm our theoretical prediction can be viewed as a success. Whether it's a real success, I think depends on whether this will eventually make it into a device that can do photovoltaics or hydrogen production at high efficiency. And this is still to be answered. So finally, let me say a couple of things that characterizes computational screening studies. So I think first of all, this is simple. You don't need fancy machine learning algorithms. It's really just a matter of sitting down and figuring out what are the key properties that you would like this material to fulfill in order to hopefully be good at the final functionality that you're interested in. So it's characterized by that there is a number of properties that you can evaluate, and typically they have different demands computationally. So stability is simple, but defect calculations are hard, so it makes sense to apply this screening approach where you start with the simplest thing to calculate, and then you narrow down your set of potential candidates. So you only evaluate the hard stuff for a much smaller group of materials. Okay, so one of the challenges in doing this is the structure. We have done plenty of other screening studies before this one where we just fixed the structure and then did combinatorial screening. This is very easy. You just take the periodic system, you replace atoms, and you have a fixed structure. That's easy to implement. The problem is you very often end up with structures that are really not the most stable type of that material. So here we looked at just 8 different structures, and that's of course an improvement with respect to just considering a single structure. But what will be another approach here, which is a more elegant approach and a more clever approach, is the genetic algorithm, and Steen will talk about that not in the next talk but afterwards. And this is also what the hands-on tutorial is about today. So genetic algorithms for structure optimization. And with that, I would just like to thank my collaborators here from CAMB, theory people, and also our experimental collaborators. And thank you for the attention.